Okay, I'm going to go through a GCSE paper, and this is January 2023, and they haven't written that it's January 2023, so let's just write that for you. So I went through this with my students recently, and this is the 1P version. I've also got the 1P regional version, which is called 1PR. So I use this as a practice run through with my students, and I'm going to go through what I went through with them so that anyone who couldn't make my live session can see what we did. So when we did this paper, I initially worked out how many marks there were for different topics. And in some of the topics, like forces, there were 3 questions which involved forces, questions 1, 3, and 5. Okay, so initially I'm going to go through questions 1, 3, and 5, and I'll explain why when I go through them. Okay, so questions 1, 3, and 5 involved forces, Hooke's law, work done, energy, as in mechanical energy transfer, so it's linked to work done, efficiency, Sankey diagrams, and equations of motion, v squared equals u squared plus 2as. So I'm going to go through those questions first, and if you're one of my students, you can use this to do your corrections, and we didn't have time to go through all of them, but in this run through I will in different parts. So this is the original formula list that was provided in the pre-COVID era, and they still include this. So I was saying one of the equations of motion which students find difficult is v squared equals u squared plus 2as, and one of these questions I'm going to go through first includes a question on this, and the rest of them I'll show you the other equation sheet that I hope I've included there. It may not have included it. Okay, so this is the mark scheme, so you can see it's January 2023, yeah, and it's the paper 1P. So this is the paper that physics students do and double science students do. Double science students only do this paper. Physics students do paper 1P and paper 2P. All right, so question 1, there's the mark scheme. Let me just pause it there in case you want to have a look at your own answers and see what they're accepting. 5-mark question. And then is question 2. Looks like I've scanned it the wrong way around. Question 1 and 2, the scanner, I've got it the wrong way around. So topic 1 is forces, and this is what we're going to go through first. Okay, so the question is on forces. Okay, so it says a material is stretched. Okay, so a material is stretched by applying an increasing load. Load means force. The material shows elastic behavior as it is stretched. What is meant? You've got to describe what is meant by elastic behavior. So elastic behavior means that the material will return to its original length or shape. Okay, you can't use any other terms other than those 2. When will it do that? When the load or the force is removed. In other words, it means it's not being permanently deformed or stretched. It's a temporary situation. So elastic means it will return to its original shape. Okay. In other words, we could say the material obeys Hooke's law. Okay. Now Hooke's law is when F, the load in Newton, is equal to the constant K times the extension X. So this is Hooke's law mathematically. They're not going to ask you that, but that means if you put the force on the y-axis and the extension on the horizontal x-axis, then when you draw it as a straight line graph, it should go through the origin. Because this says that it's proportional. Okay? It says sketch a graph for this material to show that it obeys Hooke's law. Now, Hooke's law is mathematical, and therefore, when you are showing that it's mathematically obeying Hooke's law, it must be a straight line graph, which is f equals kx. And k K would be the gradient of this graph, and K, if you like, is the stiffness of the spring. Okay? So K is the stiffness of the spring, how steep it is. So if I had a steeper spring, a steeper line on this graph, like this, so the red line would be stiffer, the spring would be more difficult to stretch. You can see it doesn't stretch as much as the green line. I'm going to rub off the red line because it's not in the question. So let's see if we can just erase the red line. So the green one is what we need to do. So because we're showing that as it's being stretched, it's obeying Hooke's law. So Hooke's law means it's in direct proportional. F is equal to a constant times x. So if you double x, you double f. If you triple x, you triple f. And in other words, it's directly proportional. You should label both axes with appropriate physical quantities. So by physical quantities, we mean force and extension. So I've put extension and I've put force. You do not need to put the units in this case, okay? Because the units, we don't know if they measured the extension in centimeters or millimeters. So axes labeled, and you can put them either way round, 1 mark. A straight line directly proportional through the origin, 2nd mark. Yeah, so straight line will get you 1 mark. If it's directly proportional going through the origin, in other words, then you'll get all 3 marks. Now, no curve is needed. One of my students said, what if we draw it showing that it curves afterwards? Well, we want to know that when it's obeying Hooke's law. So when it's obeying Hooke's law, there is no curve. Yeah? No curve needed when it's obeying Hooke's law. But if you went beyond the proportionality limit, it would start to curve like this. Okay? So it would start to curve, and this would then be called, this would be the proportionality limit. P would be the proportionality limit, and slightly beyond that, you could say it's E, which is the elastic limit. And if you go beyond E, it will no longer return to its original shape. So for example, if you manage to stretch it to here, for example, you've gone way below it, and then you remove the force, it might return to this point. And therefore, it would be permanently deformed. So the red bits are beyond the level of this question, but they could be given to you in another GCSE question. So going through these videos is not just seeing how many marks you got. And that's for Talene in particular, who said that she can't be bothered to watch the videos. Well, the videos gives you the depth of knowledge you require to improve your physics. And if someone hasn't done their homeworks all year round, and then they want to go straight into the exams and they just want to look at what they got wrong, in other words, they want a shortcut, there is no shortcut to the higher grades in GCSE. So to get the 5 marks, you need to include all the points in green and in yellow. The red bits are extra, okay? So the red bits are extra points that you can get if you're revising for another exam. So in some exams, they will ask you what happens if you go beyond the elastic limits. And that's why it's useful to listen to these videos. You can listen to them at twice speed, and you can focus in on the bits that you need the most help with. Okay? So that's specifically for Talene, who doesn't want to listen to the videos. She just wants the answers handed to her on a plate. Looks like, again, I've got the... so that's question 1 done. Now, next question I told my students to do is question 3. So I've missed off question 2, which is on magnetic fields. Okay? So question 3, the reason I'm continuing with this is the theme of forces. A winch is used to pull a truck along a horizontal road. Yeah? Horizontal means we're only pulling, the rope is pulling using a force, a tension. The winch is like a machine that kind of reels in the rope and pulls the rope gradually towards it by going on a reel. Okay, now here, forces is linked to work done, which is from the energy topic. So forces and topic 4 are often linked because when you have a machine, you're actually transferring energy mechanically. So it's a mechanical energy transfer whenever any physical work is being done, like moving an object. Okay. So as you can see, the winch is connected to the truck by a strong, thick rope. Okay. It says the winch does 41 kilojoules of useful work. Yeah. Obviously on the truck, when the truck is being pulled and it moves a distance horizontally of 15 meters. Okay. Now when work is being done, the distance must be in the direction of the force. Direction matters when we're doing work. Okay, and 41 kilojoules means 41,000 joules. Now they want you to state the formula linking work done, force and distance moved, and here you can see they are highlighting the fact that the direction is crucial. It's in the direction of the force. The distance is forwards, yeah, and so the distance is forwards and the force is along the rope, and so is the distance. So the distance moved is from where the truck starts from to the winch, okay, and the force is due to the tension in the rope pulling the truck towards the winch. So once you know that the direction matters, that's what I wanted to make sure you understood. You can then write the equation out, and the equation is work done equals force times distance moved in the direction of the force. Okay? If an angle was involved, it would make it more complicated and probably be more like an AS level question than a GCSE question. So once we know that equation, they want us to calculate the force involved. They've given us the work done, and they want us to calculate the force. So we just have to change the equation round, and changing the equation round is basically taking this equation and making force the subject of the equation like this. And once you do that, we know they've given us 41,000 from above. So 41,000 is the work done. And 15 meters was given to us earlier as well. You can see the distance was 15. So we have to put 15 in underneath 41,000. And if you do it accurately in your calculator, you can do it to 5 or more significant figures, but it's meaningless because the data provided in the question, yeah, where the numbers are given, both these numbers are only known accurately to 2 significant figures, so your answer should really be rounded up to 2 significant figures as well. Okay, so that's how you decide how many significant figures to include. So you can see how forces, work done, and energy transferred mechanically are linked. So topics 1 and 4 will, in the GCSE exam, often be linked. If you don't know how to change subject at formula round, you'll have to remember the triangles. Okay? Although they give you these equations on the more complete equation list that I've shown you, you need to know how to change the subject of the equation. They will not give you triangles. The next bit of the question says the winch includes a small engine. What's the small engine for? The engine burns the petrol, so from chemical energy is used, to power the motor. The motor uses electrical work. Yeah? So in the winch, the winch is run by an electric motor, which does the electrical work, but the energy is coming from burning petrol. Okay? The winch transfers energy mechanically to the truck. Remember, whenever physical work is done, we call it a mechanical energy transfer. Okay? So mechanical energy transfer is the useful output because we wanted to pull the truck forward. So that's our useful output. And they say the winch is only efficient to the degree of 25% pulling the truck. That means 75% will be wasted. Of what? 75% of the energy input, which was chemical. So from the chemical store that it was your input energy was chemical, 100% came from the chemical burning of the petrol, and the useful part, I'm going to put it in green, the useful output, the mechanical work, was 25%. You got to draw that to scale, in a diagram called the Sankey diagram. So the Sankey diagram is basically efficiency drawn as arrows. Okay, so how do you do it? They left you space. So originally, if this was your 100% width of your efficiency, most of it was inefficient. 25% was efficient. 75% was inefficient. That's how you could draw it. Not very well drawn. So this would be 100%, the width here. So you could draw it from here, from here all the way down to the bottom. You could draw it to scale if you wanted to, yeah? So you could draw it to scale, showing that this would be 100% of the width. This would then be, say if this was 10 centimeters, you use this. This is your chemical energy. So here you'd put chemical energy is your input. Yeah? And then your output is here. That's your useful output. That would be 25%. So if this was 10 centimeters, say, across here, then this would only need to be 2.5 centimeters. And this width here would need to be 75% the width of the original input. And this would be, this 75% would be the energy wasted. So the width of the arrow, now obviously you do it with a ruler and you'd have to label it. So it's useful output, would be labeled for your 25%. Energy wasted will be your 75%. And you need to draw the thickness of the different parts of the arrows to roughly show you that you know what you're talking about. Okay? All right, the last part of the question then goes into the winch can be used to pull the truck uphill at a constant speed. They're telling us at a constant speed. You could say if we're revising forces, it means the forces on the truck are constant. So the resistive forces would be balancing the pulling force of the winch. Okay, and then it would just go at constant speed. So that means the forward force and the backward force are equal and opposite, but you can still be moving at constant speed when the situation is balanced. The table then gives some energy stores. Okay, so here are the energy stores. And they want you to place one tick to each row. So here there's 4 rows. Chemical store, gravitational store, kinetic store, and thermal store. These are the energy stores that they want you to put a tick against. So they want you to only place one tick in each row to show what happens to the energy of each of these stores, okay, as the truck is pulled uphill. So how do you do it? Well, if the truck is pulled uphill, then the gravitational potential energy will increase, okay? Now, obviously, it's using fuel to do that, so the chemical store of energy, the petrol tank will start emptying. So the chemical store will decrease. And it's going at constant speed, remember? So constant speed means the kinetic energy doesn't change. It's going at the same speed throughout. Okay, and that's what they told you, it was going at constant speed. Now obviously the thermal store of the surroundings, whenever you do something, you will increase the heat loss to the surroundings, so that will also increase. And that's how you get the 4 ticks, to get the 4 marks. Okay, so you can see why forces and energy are linked whenever there's any mechanical work being done. The next question I asked my students to do was question 5. So here's question 3 and how they mark it. So 3A, 3B, you can see their diagram is a bit more neatly drawn than mine because they've done it with a ruler. Yeah, whereas I've talked you through it and they tell you where you get your 3 marks from. So have a look at that, see how well you did. And there is the final bit that I went through. So we want to now go to question 5. Question 4 we'll come back to. It's on radioactivity. And I didn't have time to go through it in the live lesson that I did the other day. Okay, so there's question 4 on radioactivity we'll come back to. We did it recently and we did some past questions on it for my students. So here is question 5. And this will be the end of this first part of the video. Remember, this paper 1 is 2 hours long. So this graph shows how the thinking distance, which is caused by the time to react before you brake in a car, and the braking distance, how these two vary according to the speed of the car. Okay? So obviously, before you can brake, you've got to react to whatever is causing you to want to brake. And then braking distance is the distance you travel, while braking, which is after you've reacted, Hopefully you react quite fast if it's an emergency. Now you can see that distance is on the y-axis and speed is on the x-axis. Now you can see as speed increases, the amount of thinking distance varies in proportion to your speed. So a car traveling at 30 meters per second will travel, if the reaction time is the same for the two people, for the two cars, if the reaction time of the driver is equal, then obviously if you're traveling at 20 meters per second, you're only going to travel 10 meters, whereas you're traveling at 30 meters per second, you will need 15 meters while you react. Okay, that's the reaction time of an average person, perhaps. Whereas you'll notice that the braking distance doesn't go up as a straight line. The braking distance graph is a curve. So that means at 30 meters compared to 20 meters, you can see 20 meters, the braking distance for the car would be about 26 meters. It will be around here. And for 30 meters per second, the braking distance would not be just proportionally higher in terms of linear proportional, it will be something like 50 something. So from 20 to 30, it's not just like 1.5 times as much, it's like 2 times as much. And that's because the faster you go, the more kinetic energy you got, so the harder your brakes have to work, because obviously kinetic energy is proportional to the square of the speed. And this is the level of mathematics that you need to be able to do in physics. So which of these does not affect the thinking distance? Now, the only one that doesn't affect the thinking distance is the condition of the road, because obviously the thinking distance is linked to the driver. Okay, so the driver, if he consumes alcohol, his reaction time will slow down, and that will affect his thinking distance. The speed of the car we've seen, obviously the faster the car goes, the more it will travel while reacting, because obviously if you're driving faster and you're thinking the same speed, you will go further if you're driving fast. And of course, the tiredness of the driver also affects his reaction timing. So the answer is B, the condition of the road does not affect the thinking distance. And then which of these increases the braking distance of a car? Okay, a faster reaction time Yeah, well, that doesn't affect the braking distance at all because it comes on before braking. Okay? Whereas ice on the road, of course, makes it more slippery and it will increase the braking distance. So it looks like B is the answer. Let's just go through them. More powerful brakes. Well, if they have better brakes, it will decrease the braking distance. So don't get confused. And if you have tyres which have more grip, better tyres, will also decrease your braking distance. So the answer is B for these 2 marks. It's a very common question in paper 1. So here's the mark scheme for A and B, and here's the mark scheme for the parts I haven't shown you, which are more mathematical. Here it tells you need to know the stopping distance is the thinking distance plus the braking distance added together. So there's 2 bits to stopping a car. Thinking about stopping and physically braking and doing work against the movement of the car. So part C is about stopping the car, and part D then goes on to do a little bit more mathematics. Yeah, so we'll come back and look at it. So you can go back to this video and stop and see how they are marking it. And there's part E as well, where we're going to use the equation v squared equals u squared plus 2as. Okay? Okay, so it says determine the stopping distance of the car when the speed of the car is at 20 meters per second. So you've got to get it from the graph. There's 2 bits to get from the graph. Yeah? Remember we said the stopping distance, yeah, involves both graphs. Stopping distance equals thinking distance. So from the graph you've got to look at the thinking distance and you've got to look at the braking distance. So again, from the graph, you've got to look at both of these and you've got to add them together to work out the stopping distance. So what we're doing, we're looking at 20 meters per second. So we're going to go all the way back to the graph. And you can see at 20 meters per second, you need this value and this value to work out the total stopping distance. So over here is 10. The distance you travel while you're thinking, and then once you do that, you've got to add the braking distance for the speed here, which looks like it's this line, looks like it's 26. So 26, add the 10 to it, you get 36 meters altogether. 10 meters traveling while you're thinking about braking, and 26 meters required for your brakes to bring the car down to 0. Okay? So that's how you get here 26 meters. Okay? 10 meters thinking and 36. 26 meters was braking and thinking distance was 10 meters. So you add them together and you get 36 meters. Okay, the next bit of the question wants you to state the formula linking average speed, distance moved, and time taken. Average speed is the total distance moved divided by the total time taken. Okay? Now normally distances we use S. Yeah, it's commonly used in physics. Average speed, I put a little line above V for velocity. Okay? Now, determine the reaction time. So we want to work out time, okay? So if we want to work out time, we can use this triangle, yeah? And we want to show that time is equal to S over V. So time will be distance traveled against speed. But we want the reaction time. So we got to use the graph, which is a straight line graph, which shows a reaction timing. Okay, so that's the one we want to use. So you go back to the graph and you can take any 2 values, any 2 corresponding values, So I did, for example, at 20 meters per second again, I saw the distance was 10, which we used in the question before. So if you see what the reaction time is, so the reaction time would be the distance traveled in the straight line graph, yeah, divided by the speed that you're traveling at. And because it's a straight line, any two corresponding values will give you the same reaction timing. So that straight line graph shows the reaction timing as the gradient, okay? And they're giving you the units, so you don't have to worry about that. The next bit of the question wants you to use the equation that I showed you, which is v squared equals u squared plus 2as. So when do you use this? Well, we use it when we don't know what the time involved is. They want you to calculate the acceleration, the braking acceleration. So when the car's braking, yeah, as it brings the car to a stop, we know that the final velocity, which we normally symbolize as v, using a letter v, from the initial speed, which they tell us was 30. So if you remember your SUVAT, we call these the SUVAT equation, S, U, V, A, and T, yeah, where S is distance, U is initial speed, V is final speed, A is the acceleration. So we want to work out A. Now we know V was 0, will be 0 because it's come to a stop. We know U is 30 meters per second because they told us. We don't know A, we want to find A. And we can work out what S is. We can work out what S is from the graph. Which graph are we talking? We're talking about the braking graph, because we're talking about as it brakes. So the graph you need to look at, yeah, at 30 meters per second, yeah, is the curved graph. And once you look at the curved graph at 30 meters per second, go and have a look, you should be able to work out that the distance traveled for a car going at 30 meters per second while it's braking, for that graph will be 53 meters. Okay? So once you know it's 53 meters, we know we can put the values into this equation, and therefore we know V, we know U, we know 2, we know S. The only unknown is A, yes? So if you know how to change the equation round, it would be V squared minus U squared over 2S. Now the V was 0, the initial speed was 30, so you've got to square those. 0 squared is 0, 30 squared is 900. You notice that it's decelerating because there's a minus sign. 0 minus 30 squared will give you a minus 900 at the top. And 2s at the bottom is 2 times 53. And s, remember, we got from the graph. So it would be 2 times 53 is 106. And I think if you do that, the acceleration will become minus 8.5 meters per second squared. Now, they've given you the units. So you can see now we did 3 questions from one paper. The total number of marks in the paper is out of 110, and we've already done 29 marks. So questions 1 to 3 in this exam are worth nearly 30% of the exam. So you can see how big a topic forces is. Forces, motion, materials, yeah, and therefore doing work requires a force. Well, that's the end of the first video. Hope you found it useful. Don't forget to like, share, and if you haven't subscribed, make sure you subscribe because I'm putting more videos up. Next week I'm starting on 2024 videos, and I have other videos to put up as well when I get the chance to. Okay, so if you subscribe, you'll be notified if you've hit the notification bell. And if you're one of my students, you're meant to keep a record of all the past papers you've done and to do your corrections in purple. So remember, we use the purple for making sure you've improved it. So hopefully you find my explanations clear and useful, And all I require from you is a thank you by showing me a like and leaving me a nice positive comment. Thanks for watching. See you in the next video. Bye for now.